Hello there, and welcome to another tutorial. My name is Tanmay Bakshi, and today we'll be diving into the JAX library. Now, what is JAX? Well, to quote them right off their GitHub repo, JAX is a Python library for accelerator-oriented array computation and program transformation designed for high-performance numerical computing and large-scale machine learning. Now, that's a lot of big words, so to sum it up, it's an ML framework. It's like PyTorch and TensorFlow. It enables you to train machine learning models and, of course, do a lot more interesting stuff, but that's what I'm primarily interested in, and that's what we're going to be diving into today. Now, if you've seen other videos on this channel, or if you've seen my open source work, you know that I usually use PyTorch. That's the framework that I've been a fan of, and before that, when I was relatively new to the world of ML, I used to use Keras. Now, throughout my journey of learning machine learning tech, I've switched between different frameworks a bunch of different times, and for different tasks sometimes call for different frameworks. For example, TensorFlow is not usually a framework that I use every single day or like in my day-to-day work, but if I ever need to train on a Google TPU, for example, of course I would use TensorFlow because as anyone who's tried to use PyTorch XLA will tell you, it is absolutely painful to try and use PyTorch with TPUs. However, the goal of JAX is to sort of, I would say, fix almost a lot of the mistakes that the machine learning industry has made in the development of these frameworks, specifically to do with actually training them at genuinely a large scale and training truly complex models. What do I mean by this? Well, first of all, before I dive deeper into JAX, one thing I want to start off by saying is that today we're going to learn a little bit of JAX by actually implementing a real machine learning model for handwriting synthesis. So the idea is that you can provide some text to the system and it'll use a neural net to generate handwriting by like actually drawing out text based off of the characters you give it. Now, to do so, we're going to be taking some inspiration from a paper published back in 2014 by Alex Graves from the University of Toronto called Generating Sequences with Recurrent Neural Networks. And in this paper, Alex goes into detail on an architecture for a recurrent neural network that can generate handwriting. And inspired by that architecture and the way that it works, including its dataset, we're going to train something similar today, except a little bit more modern. We're going to use transformer blocks and so on. It's going to be a really interesting comparison. So we're going to build something that is real world applicable. It's a genuine use case. But sort of back to what I was saying about why JAX even exists. Why do we need another machine learning library? Well, it's because if you take a look at the history of ML frameworks and you go all the way back to the TensorFlow version 1 days, you'll realize that back then people really kind of despised the TensorFlow APIs. If you go back and see some TensorFlow v1 code for anyone who hasn't yet, you'll see what I mean. It's incredibly archaic, by today's standards at least. The idea of TensorFlow v1 is that you would construct all of your tensor operations as a graph manually in Python code. So what that meant is that you were almost meta-programming in a way. You were writing Python code that itself was responsible for invoking API calls within TensorFlow and its runtime to help it construct a graph of all the different tensor operations that describe your math. So if you wanted to do x times y, you couldn't just take two tensors and do x times y like you can today with PyTorch or even TensorFlow v2. Instead, what you'd have to do is you would have to create placeholder tensors for x and y, describing their shape and data type. You would then need to manually construct a graph where you added this multiplication operation to the graph, and then you would compile this graph of operations, and then you would invoke it directly by passing it actual tensor objects. Now, arguably, there are some advantages to doing it this way, there's some disadvantages to doing it this way, but in retrospect, the only reason I today can really understand TensorFlow v1 code is because I not only have more experience with machine learning, but I also have more experience with compilers and other low-level technology. In fact, the way that I usually describe TensorFlow v1 these days is almost like the LLVM IR Builder API. It's almost like you are, again, as I said, literally manually meta-programming your operations into a TensorFlow graph. Now, because that was so archaic and because people really didn't like that API, it was not flexible at all. It didn't feel Pythonic. You were writing code to write code. PyTorch got really, really popular. And the idea of PyTorch was to do eager computation. So instead of having to construct a graph ahead of time and then compile it and then execute it, the idea of PyTorch is that you have these tensors, and every time you run an operation, PyTorch is instantaneously dispatching kernels onto GPUs or just even on your CPU, running the math to give you those materialized tensors. And of course, this is so much more flexible. The API is so much cleaner, neater, actually. But then the problem is performance. And performance suffers when you do this because there are so many optimizations that you can exploit if you already know all the operations that you're going to run in advance. Now, there are, exceptions and asterisks everywhere here. I'm sort of oversimplifying. But really, when you start to train super large-scale machine learning models with PyTorch, things start to get a little bit finicky. For example, inside of a convolutional neural network, or inside of a transformer, where you have your primary convolutions or matrix multiplications, then you've got your activation functions. A lot of the times, you could do things like fuse together those different invocations to your accelerators and make it a single invocation, compile it down to be more optimized. Or potentially, if maybe you decided to write code that was maybe a little bit more explicit and did more math, but could have mathematically been simplified to simpler operations that are just a bit harder to write in code. In PyTorch, you'd have to choose between writing code that is harder to read but mathematically faster, or simpler at least, or having to write more readable code that unfortunately just won't run as fast. And so PyTorch has all kinds of workarounds to try and get around this exception, this sort of like performance case. Originally, it was TorchScript and their just-in-time compilation abilities, and eventually some ahead-of-time compilation abilities. And then with PyTorch 2, they released the torch.compile function, which there's a lot of hype around it when it initially released. I was super, super excited. And Torch Compile has been really nice, but as unfortunately a lot of similar attempts as Torch Compile in the past, it's not super robust. It just doesn't actually end up working in the real world a lot of the times. I've had cases where I'll take a model that hasn't been torch compiled and it'll work just fine, but then I torch compile it and suddenly it's a lot faster, but I'm starting to get not a numbers in my losses, and I'm starting to get spikes, and things just clearly aren't exactly the same internally as they were before. And so that's a problem. PyTorch suffers from these performance issues and also these stability issues when you hit the corner cases like trying to compile PyTorch code. And all of this is made significantly more complex by the fact that this is all in Python in the first place. Python being this super dynamic, fuzzy interpreted programming language means that you can do all kinds of things to the interpreter to mutate state at runtime and do all kinds of weird things that these ML frameworks can't necessarily fully deal with and compile ahead of time. And then that finally brings us over to one more, I guess, corner case that has been traditionally really difficult to cover, and that's really large-scale distributed training. That's not something that I necessarily do day-to-day either. I do have experience with it, but that's something that's more rare, which is why you maybe don't hear about it as much. But when you use PyTorch, TensorFlow, and so on, well, TensorFlow less so, but PyTorch especially, and you train on really large clusters, of course it can be done. That's why we have all these different models like Llama and so on. But it is really difficult. It is hard to comprehend exactly how to use the PyTorch APIs in ways that allow you to, for example, shard your computations onto different machines in a big cluster if you're training super large machine learning models and so on. Finally, though, that brings us to JAX and why it exists. JAX is a machine learning framework that takes a very fundamentally different approach to almost everything than all these other frameworks, and I don't like it in some ways, and I do love it in some other ways. The core idea behind JAX is that it is a functional API. Everything boils down to being as functional and effectively stateless as possible. JAX avoids mutation pretty much everywhere. Like, for example, with TensorFlow and PyTorch, you can mutate tensors, you can set values at certain indices. Technically, in JAX, you can't even do that. When you do that, you are explicitly using syntax that means that you are creating a copy of that array. In fact, sort of getting the terminology as well, JAX doesn't even call these arrays tensors, they call them arrays. Their APIs are modeled off of NumPy, so if you've ever used NumPy, then they're going to seem very familiar to you. In fact, I'm quite certain that a large majority of the actual API coverage is the same across NumPy and JAX. Apart from that, JAX supports all kinds of really fun utility functions that you simply cannot support unless you have the inner machinations of JAX powering it. For example, one of the things that really bothers me about having to write ML models in other frameworks is dealing with batch dimensions when you're working with models like transformers. Dealing with the batch dimension is another axis that you have to wrap your head around and how you're actually moving it around, where it is in all of your arrays. It's a little bit annoying to have to deal with. But with JAX, you can actually write all of your code to not care about a batch dimension at all, only thinking in single samples. And then when you finally actually invoke your machine learning models, you can use this thing called the vmap in order to tell JAX to vectorize, that's what the V in vmap stands for, to vectorize your computations across a new axis. And because JAX is entirely this functional compiled paradigm, it will actually then trace through all your different operations and figure out how to efficiently introduce this new axis of computation into the graph without doing like a naive for loop, for example, right? If you were to manually invoke this model, n number of times where n is the number of samples in your batch, that would be incredibly slow. But JAX is doing a much smarter approach where it's really understanding how do we compile this graph to be efficient in a vectorized manner across this new axis. So there's all sorts of fun things JAX lets you do, and I think it's just best if I were to show you how JAX actually functions instead of just talking about it. As I mentioned, it's a very different paradigm. It's one that takes some getting used to. I'm still getting used to it, but over this video and the next couple videos that I release, I'm hoping that we can sort of learn JAX and start using it to train some larger scale ML models. So let's get started with a super simple example of how you can use JAX's just-in-time compilation, JAX's vmap functionality, and just generally what the API surface looks like, and then we'll get into actually training the model. So without any further ado, let's dive into it. All right, let's start with a super simple example of JAX in action just to get familiar with the syntax and the paradigm. Now, as you can see, I've got a simple Colab notebook up here where we're going to experiment a little bit, and I've already got some imports in. The one that's most interesting right now probably for you is this one, line 2, where we import jax.numpy as JNP. Under that JNP symbol, we have access to an API that is effectively NumPy, is what it is. There's a lot of overlap between the NumPy APIs and this one, so you'll have a lot of familiar syntax, like I could say, for example, x is equal to jnp.array5, y is equal to jnp.array6, and suddenly I've got these two values here. Just like NumPy and just like actually tensors in PyTorch and TensorFlow, these arrays don't necessarily need to be literal arrays like lists. They could even be, for example, scalar values. So think of JAX NumPy arrays as the equivalent of a NumPy array or a PyTorch tensor and so on. So declaring those two values, just like that, I've got my first JAX NumPy arrays. Now from here, let's define a simple function so we can actually do some interesting math. I like to write Python with type annotations, so I'm going to continue that sort of pattern here. Say we create a function called foo taking two arrays, x and y, and also returning another array. Say within here I wanted to maybe print foo call, and you'll see why this is important in just a moment. I can then go ahead and return x times y, and there we go. We've got a function that performs some simple arithmetic. Now, one of the nice things about JAX is that I still haven't lost the ability to do eager execution, kind of like PyTorch allows me to do, or TensorFlow v2, despite the fact that JAX also gives me lots of interesting compilation abilities. So if I want to call foo right now with x and y, it'll just work. It'll print foo called, and it'll give me my array 30. I can call it again, and the exact same thing will happen again. It'll print foo called, and it'll give me 30, just like you would expect. This is just normal code so far. But let's take a look at the first sort of interesting feature that JAX gives me that you don't get out of the box anywhere else. And that is JIT compilation for performance. So watch this. If I say foo JIT equals jax.jit foo, what I've done is I've effectively created a new function called foo JIT, and it's wrapped this foo function that I already had using JAX's just-in-time compilation infrastructure. So what does this mean? Well, foojit, as I mentioned, is a function, and I can still call it just like I did before with my values x and y. If I call it, you'll see what you would expect. You'll see it prints foo called, and then you'll see that it gives me my array 30, and that's my result. But what happens if I call foojit one more time? Well, let's find out. I pass it x and y. It's a little bit weird. I only get my result, 5 times 6 equals 30. I don't see foo called anymore. Why do I no longer see foo called? Well, when I wrapped this function in this jax.jit wrapper, what happened is JAX was told basically that whenever we invoke this function, we don't want to be calling all the Python code necessary to do so. Instead, we want to call a compiled version of the function that has been optimized for whatever hardware we're running on and whatever operations are being performed within that function. Now, why does that result in foo called not being printed? Well, it's because previously, when we were invoking the foo function directly, we were performing eager execution, as I was mentioning. We were genuinely invoking this Python foo function, which was genuinely invoking Python's print function and also genuinely returning the multiplied values of x and y. However, when we ran this foo JIT function, the first time, we were calling into JAX and saying, here's x and y, I need you to compute the result and give it back to me. And the first time we ever ran that code, JAX actually had to call foo normally, as if we hadn't wrapped it in this JIT wrapper. The reason JAX had to do that is because first it had to run all of your Python code normally so that it could trace through your Python code and figure out what operations you're even running in the first place. Because just doing this, JAX actually doesn't know what the foo function is going to do internally. And that's due to the sheer complexity of the Python programming language and just how hard it is, if not really impossible, to fully ahead of time determine the behavior of Python code and what exactly will be done to your variables and your inputs. So just this line of code was insufficient for JAX to be able to determine how to actually compile this function. In order to compile that function, JAX actually had to look at some input first, run it through that function, and then once it was run through the function, it would take a look at the output, and it would take a look at the graph it was constructing internally as that function was executing. It takes a look at all those operations, and then it compiles it. So the first time we ran the function, it actually wasn't invoking a compiled variant, it was invoking the normal variant and tracing what happens internally as it executes. Then, when it was done, JAX internally stored a pointer to a compiled version of the function that contains optimized instructions for your hardware and dependent on the operations that were traced within foo. Then the next time we call it, JAX remembers that it's already figured out how to compile this function, and there we go, it gives us the result, but it doesn't print foo called, and that's because, well, JAX isn't running Python anymore. That's one of the things you gotta really keep in mind when you read and write JAX code. This function foo, when I go through these sort of like function transformations through JAX, especially JIT compilation, we are getting rid of all the Pythonic stuff, and we are only keeping this graph of operations of what JAX wants to do, or what the JAX arrays are doing from an arithmetic standpoint. And so that's one of the things that you do need to be careful of. But this gives us some really cool capabilities. Like if foo was significantly more complicated, had tons more variables, large-scale inputs, the JAX JIT compilation would help us a lot with performance. And you'll see what I mean later in the video of a comparison of using JAX JIT and not using JAX JIT. It's a huge difference in terms of practicality for training large-scale models. Now, JAX-JIT isn't the only interesting thing JAX can do to your functions. There's another one that I think is even cooler in some ways, and it's the ability to vectorize operations. What does that mean? Well, say x and y weren't just scalar values. Say they were actually they were actually vectors. So maybe it's like 5, 3, 2, and 6, 0, 2, or maybe 4, right? So we've got two vectors now. The operation within foo here is pretty simple, and it will very simply broadcast across x and y here. So if I just invoked foo with x and y again, you would see that it just works because it'll do an element-wise multiplication. But what if our function was a little bit more complicated and the operations wouldn't just broadcast like this? Say I imported the einsum operation from einops. And then say I declared another function called bar. We're going to take x and y again as our arrays, and this time we're going to perform a matrix multiplication. So this is going to effectively act as almost like a linear layer, except without like a bias. And the way we're going to do it is we're going to perform this einsum. We're going to expect that x only has one axis, and that will be, say, d, our dimensionality. Or say actually our input dimensionality. Y is our matrix, you can think of it as our weight matrix for the linear layer. So it has our output dimension, our input dimensionality and our output dimensionality, and we're going to transform this into just output dimensionality. So this is the Einstein notation for performing the correct matrix multiplication necessary to make this act as a linear layer. So passing it x and y, making sure that it expects the tensors first, passing it x and y, this should perform the way we expect it to. So if I said that x is equal to j and p array, say simply 5, 2, and I said that y was a weight matrix. Our input dimensionality here is 2, and our input dimensionality is the outer dimension. Say our output dimensionality is 3, so I can simply say 1, 2, 3, 4, 5, 6, so this is a 2, 3 weight matrix. I can then go ahead and pass these both to bar, and I should get my output dimensionality of 3. Give that just a moment to execute, and there we go. So I get my output dimensionality correctly. Now, if I were to simply say, hey, I have multiple values of x. So instead of just 5, 2, imagine x was now a matrix or I had 5, 2, and also, say, 6, 1. And I wanted to run the same operation, x against y, einsum is now going to complain, because suddenly x has more dimensions than we initially declared. But what if I still wanted to vectorize this operation such that we can pass in multiple samples through this x value, run them all against the weight matrix, and get my output, but I want to do it in an optimized way. I don't just want to for loop it, because then I'm not taking advantage of my underlying accelerators. There's ways that potentially these operations can be fused into one. In fact, I know for a fact that matrix multiplication can. So how do we make this happen? Well, pretty simply, instead of just calling the bar function naively, what we can do is bar vmap. We're going to call the jax.vmap function, and we're going to pass it the bar function. What this is going to do is it's going to vectorize this function across some certain axis. And we can tell JAX which axes and which parameters to vectorize across. So in this case, I know that I want to be able to pass multiple samples through X, but I still only want to have a single weight matrix Y that I actually perform the multiplication against. So I can specify to vmap the in-axes as 0, none. What that's saying is I want to vectorize across the 0th axis of this x, which is the first argument, and we do not want to vectorize across the second argument, which is y. That's why we're passing it none. Now by default, it will do the first axis, meaning the 0th axis of all inputs, but in this case, the reason I'm specifying it is because I don't want to vectorize against that quote-unquote weight matrix. So executing this gives me a new vectorized version of the function, and watch this, it's like magic, I love this stuff. If I just pass it x and y now, in theory, it should go ahead and give me, just like that, the data we expect. 13, 20, 27, just like before, 13, 20, 27 corresponds to the 5, 2 input, as we saw, 5, 2, 5, 2, 13, 20, 27, and then 6, 1 corresponds to that second input that we were passing it. And just like that, the code that I wrote internally, this bar function, does not need to worry about the existence of that batch dimension. The code inside of it is fully invariant to the idea that that axis exists. It doesn't see it. Like inside this function, if I were to do a print x.shape, I still wouldn't see that axis. But JAX figures it out. JAX figures out how to modify these operations internally to support that new axis. And then, best part about it is that because JAX is internally consistent with its abstractions and the way that it represents these operations, you can compose together all these different kinds of JAX transformations. Like now, for example, I could say bar vmap jit equals JAX jit bar vmap. And just like that, I've now JIT compiled that vmapped function. I can now pass it x and y. First time, of course, it's still going to compile, so it's going to be a little bit slow. Second time, it should be practically instant. Again, in Colab, and because of the fact that this is such a small function, you probably won't notice it. But again, later in the video, we're going to see how with really, really big functions, this makes a really big difference. And so that's the interesting part about JAX. Everything's internally consistent, things compose with each other, and the knowledge that JAX has of the inner workings of your code because of the fact that it's doing that complex tracing allows it to do really fun things like this vmap capability, which it's really hard to overstate just how cool it is when you're writing real-world ML code. And one last little quirk that I want to talk about is the way that JAX deals with random numbers. Now, because of the fact that JAX, its entire paradigm is to sort of keep functions pure, to make it so that everything is stateless, so for example, passing the same function, the same parameters, theoretically the idea with JAX is that every single time you should be getting the same output. That makes dealing with randomness a little bit difficult, because fundamentally, randomness deals with some kind of external state that you're dependent upon, like a random seed. And it's a big problem in the ML, I guess, field, the fact that it's hard to reproduce experiments a lot of the time, not just because sometimes, say, papers underspecify what they did, but also because of the fact that random seeds are actually surprisingly hard to set. Especially in large-scale distributed environments, it's hard to have a clear picture of what libraries you're using, where you need to set all your random seeds, how to get your behavior to truly be deterministic. It's honestly next to impossible with a lot of other frameworks. With JAX, it's actually really easy. Sometimes, though, I can admit it can be a little bit cumbersome. Let me show you what I mean. So the way that JAX deals with randomness is using keys. These keys are effectively your random seeds, and they have to be passed around manually everywhere. Sounds worse than it is, though. Here's an example. So to create a JAX random key, I can simply say key equals JAX random PRNG key, and pass it a super simple random seed, say 42. Classic. From there, I can create my random numbers. So JAX random normal, I can pass it my key, and I can also tell it what shape I want. So say I want a shape, an array of shape 2, 3 again, just like that, it will give me that array. Now, thing about this though is that if I were to simply call this function again with that same key, I'm going to get the same random numbers because, as I mentioned, the key is the seed. And so you need to make sure that you're cycling that seed over and over again. And this is where the cumbersome part comes in. In order to help you cycle this key and get new random seeds, you have to perform what's called a split. So generally, the sort of, I guess, standard for the way this is done in code is splitting the key into a subkey. So you'll do jax.random.split key, and that'll give you back 2 keys. You'll usually store one back in your key variable and then store a subkey, which is the one that you'll actually use for your random number generation. This way, as you can see, I got different weights than the last time, right? And if I run this exact same code snippet again, I will get different weights than even this time. There we go. Because here I split the key into a key and subkey, use the subkey. That means both of these were different than before. Splitting it again gives me yet another different subkey that I can use to generate the random, and I still have this pure key that hasn't been used yet that I can then split further in the future when I want to use it and use a subkey. So that's sort of like the standard of how you use create randoms in JAX. You can also split into more subkeys, like you could say subkey 1, subkey 2, and pass it like 3 here, saying that you want 3 keys as output. But yeah, that's just a quick primer on random numbers in JAX, vmap, JIT, how it all works, at least externally. Now let's get into actually training our handwriting synthesis model and at least what the architecture looks like. All right, next up, let's talk about the data for the model we're going to train today. Now, heads up just in advance, today we're not going to be training a conditioned handwriting synthesis model. What that means is we are training an unconditional handwriting synthesis model. Effectively, this model won't actually know what it's writing, and I know that sounds kind of weird, but what you're seeing on screen right now is an example of a generation from the model that we're going to train today. You can sort of probably tell what it means to be unconditional now. Effectively, the model doesn't actually have specific characters that it's going to try and write when we get it to write things. It's going to basically just hallucinate what handwriting looks like to someone who doesn't actually know that they're writing specific characters or that there's a thing that they're supposed to be writing. Now, I don't mean to anthropomorphize the model here, but effectively that's what it's doing. It's hallucinating handwriting. That's just for simplicity, and in the next couple of tutorials, we're going to make this model more advanced incrementally to get it to support conditional generation and theoretically more things like specific handwriting styles and so on in the future as well. For now, though, let's take a look at the data that's necessary for today's task. Starting super simple, data class to represent a point, just an x and a y coordinate in the lines that the model is going to draw. From there, we've got the idea of a stroke. A stroke is a continuous series of points that are drawn by a quote-unquote pen. So right as a pen is put down on a quote-unquote like metaphorical piece of paper, that's the first point in a stroke. As the pen moves along the piece of paper, more and more points are registered. When the pen is lifted from the paper, that's the last point in a stroke, and that ends a stroke. From there, we then get into a stroke set. A stroke set is a series of strokes that are disconnected, and that represents, for example, a sentence. So a sentence is a series of strokes. We call this a stroke set. Stroke sets can either be absolute or they can be relative. I call relative stroke sets normalized stroke sets. What does that mean? Well, a normalized stroke set is where you effectively take every single point in the stroke set across strokes, so not just individual strokes. And each point, its coordinates, are set instead to be offsets from the previous coordinate. So the very first point is set to be x equals 0, y equals 0, and then from there, every other point in every stroke is equal to the previous point offset from to where that point would be. So that means that the very first point in, say, the second stroke is going to be equal to the offset from the last point in the first stroke. So that's just to give you an idea of how we normalize this data. This is important because when we train the model, we don't want it to have to memorize the coordinates on the specific whiteboard, for example, that the data was captured from originally. We want it to more generally understand that when you start writing, you're moving the pen based off of where you were before, not to very specific absolute coordinates on the canvas that we were using in the data set of handwriting data. I've also got a nice utility function here to render the actual strokes. So what this will do is it will take the stroke data and it will render it out so you can see samples from the data set or samples that the model generates. What you're seeing on screen right now are a couple of samples from the actual data set that we're using, the IAM online handwriting database. We're going to use this to train the model. There's also another function here that encodes the data inside the stroke set as a series of time steps that are compatible with our model architecture. We'll talk more about the model architecture in just a moment, but what you'll see here if you take a look at this data is that it's actually really, really simple the way that we encode it. Effectively, each time step input to the model just has three values. The X and Y offsets from the previous position, so exactly what we just talked about, and also a third integer which represents whether or not to lift the pen at that time step. So the idea is that for a time step output by the model, this third value will represent Boolean true or false should the pen be lifted up after this point to start a new stroke. If the value is equal to 1, then the next point that is output by the model, the next prediction the model makes, will be considered a new coordinate as part of a new stroke, not a previous one. So this allows the model, for example, to lift the pen between characters, or for example, to lift the pen to dot an I or cross a T, things like this. Now, there are a couple of quirks with the way we handle this right now. For example, a slight deviation from the original paper that I have here is that in the very last stroke in the stroke set, instead of the value of this being 1, I actually set it to 2. And the reason that I do that here, the reason I set it to 2, is because I want to model the idea of the end of the stroke set as well. So 0 means keep the pen down, 1 means lift the pen, but we're going to put it back down next, and then in the next step. And then 2 means lift the pen up and we're done writing now. So that's a slight deviation from the paper, and we don't actually use this functionality yet, but it's going to be useful in the future when we want the model to generate specific sentences. And then I also just have a function that does the inverse of that, that goes from time steps back into an actual stroke set, and this is so that we can take the output of the model and use it to generate predictions to actually visualize what the model outputs. And we've got a little bit more code here, but we don't need to worry about that just yet because we're not doing conditional generation. I've also got a script here that will read the IAM on DB database, load all the data, all the different stroke sets and the transcriptions, and it will go ahead and save them, and also just print some stats about, for example, how many characters per sample there are, how many points per stroke, and so on. This specifics of this code aren't super important to the model or to JAX, which is why I'm not going to go through it in too much detail, but again, the code is available in the description below for you to take a look at and study in more depth. The thing is that this code will be different depending on which data set you're using or how it's formatted, which is why I'm not going to go into too much detail about it just yet. But now, let's take a look at the actual model architecture. So taking a look at model.py, as you can see over here, I've got what's called the unconditional handwriting model, and already you're going to start seeing some familiarities here. For example, it's a subclass of eqx.module. eqx is the Equinox library. Now, Equinox is a JAX machine learning framework, and the reason that I'm using it is because it is an incredibly simple abstraction over JAX. I don't mean incredibly simple as in it's not useful. Equinox is a great library. But what's really nice about it is that it doesn't do really anything extra that you couldn't have already done yourself without JAX. And I guess that technically speaking, that's strictly true about every library. PyTorch is just doing things that you could have done yourself in like C++ and CUDA. But what I mean by that is that they aren't fundamentally modifying JAX in any way or giving you functionality that wouldn't be compatible with the rest of the JAX ecosystem. Now, the majority of people that train machine learning models with JAX today use a different library called Flax. In my opinion, though, Equinox is a lot more ergonomic in the sense that it's not redoing things. For example, Flax has its own functions for JIT and for vmapping and so on, because there are some quirks to the way that it works and how it interacts with JAX, preventing it from being compatible with a lot of other random JAX code that you might find on the internet. Equinox, however, is very mindful of effectively just providing you some convenience functions. That's effectively all Equinox is it's all conveniences on top of JAX instead of genuine extra logic, like heavy runtime running on top of it. So let's take a look at how this module works and what the differences might be compared to something that you might be more used to, like, say, PyTorch. So this unconditional handwriting model here, as you can see, inherits from EQX.module. One of the interesting things about this is that this class instantly becomes a data class. It's also not meant to be stateful. So unlike, say, a PyTorch module, the idea behind this model is that it's not going to contain any persistent state like Python objects and stuff. The only real quote-unquote state that it will carry are its weights as in the form of JAX arrays. And that might not be directly in this model. It might be down inside of its layers. For example, this linear layer has its weight matrices and stuff. But when you boil it down, all of it sort of turns into these leaves, if you think of it as a tree, where these leaves are either JAX arrays or things that are like JAX arrays, or they are fields and data classes that have been set to be static or handled in some way. For example, the dimensionality of the model, that's something that I'm storing as part of the model under this dim field. But what I've told Equinox is that this is a static field. It's not something that we want to optimize. It's not something that JAX needs to care about. It's a static field that we're storing as sort of the metadata of the model almost. And this is important because the way JAX treats models like this are as what it calls pie trees, and that's why I'm using the tree analogy. The pie tree enables JAX to look at this model and sort of map out all the different weights and other things that it needs to worry about for things like optimizers, for checkpointing, for computing gradients, and so on. Even sharding. So for example, if I took this model and I sharded the weights across different accelerators, having this pie tree view of the model is what enables JAX to actually do that. Otherwise, it doesn't know how to look into your model and find your weights and so on. So right off the bat, that's one of the differences to keep in mind. I'm also just declaring what layers I'm going to use, but we'll get to that in just a moment. We can also skip, for example, the initializer here. Let's just get directly into the meat of the function. So super simple beginning of this architecture. We have an input projection. It takes those three parameters I was talking about before. It takes our x offset, y offset, and our pen lift value, and projects it up to the dimensionality expected by the model. After that input projection, we've got a couple of multi-head self-attention blocks. So basically super simple transformer architecture, just like sequential. We've got a couple multi-head self-attention blocks, a final layer norm that we're going to perform on top of the output of those blocks. Then we've got a Gaussian mixture model. What does that do? Well, this is the output layer that enables the model to actually represent where it wants to move the pen after the current position. The reason we're using a Gaussian mixture model instead of just projecting back into two coordinates is because, well, handwriting is complex. At any given point of where the pen currently is, there is not a single correct answer as to where the pen should move next. There are many possibilities depending on handwriting style, depending on just random chaos. It's highly variable. And so we would not get good performance if we simply train the model to predict exactly where to move next. Instead, what this Gaussian mixture model enables us to do is have the model output the parameters of multiple different Gaussian distributions. So we have this model output the mean, standard deviations, and correlations for many different distributions, and we call these distributions components. So these are different components. That's why you see this n components value. And all of these different components represent different probabilities of where the model believes the pen might move to next. And the model will also output probabilities of which of these components to choose to sample from. So this is a really convoluted way of effectively saying that the model will output the parameters for a distribution that we can then sample our two-dimensional point from. This lets the model make sort of like a fuzzy prediction instead of forcing it to make a single real-valued prediction, which really just wouldn't result in very good performance. So this basically makes it so that while all the model behavior can be deterministic, this final output layer enables us to then perform some sort of like chaotic stochastic sampling of points out of the model, meaning the model doesn't need to, well, model that for itself. So this mixture model will help us perform that sampling, and then we've got this Penn state projection, which is just a super simple multi-layer perceptron to go from the dimensionality, which is the output of our transformer, to one scalar value, and that one scalar value is the regression target of should we lift the pen or not. That's it. Now, so far, hopefully so good. You can probably start to notice some of the JAX patterns here, like for example, all the layers that require some kind of random initialization. They're getting these subkeys in so that they can actually do this random initialization. Layers that don't require it don't get the key, like layer norm. Its weight initialization is known constant. The weights are equal to 1, the biases are equal to 0, and therefore it doesn't need a key for random number generation. This is what enables you to have this sort of repeatability that the JAX community really likes, right? Like if I start my program with the same random seed, then we're just fundamentally always running the same random splits and the same, same random number generation. And so we will always end up with repeatable experiments without needing to do super complex massaging of different libraries and making sure they all work nicely with each other. From there, we get into the loss and sampling functionality of the model. Before we dive into that though, let's take a look at the implementations of these layers themselves because I think it's actually really cool the way that it works. The multi-head self-attention block itself is super simple. It's what you would expect. You've got your attention and your attention norm, and you've got your multi-layer perceptron and its norm as well. Now, the thing is that this is a pre-norm transformer, meaning that we perform the normalization on the input and then run attention and the multi-layer perceptron and then have our residual connections, unlike a post-norm transformer. But take a look for just a second at what this line is doing here. It looks a bit convoluted, so let me split it up for you. I'm going to take this first parameter, and I'm going to split it up into another value. We're going to call it y for just a second. We're going to pass y back into the attention layer here. So think about, for just a moment, what the shape of our different arrays are. So x is the input to the block, and it's of shape n time steps, and then dim. So dim is our dimensionality of the actual tokens themselves, and n time steps is the number of time steps that we are taking a look at in the sequence. Now, as I said before, the majority of JAX code, including Equinox code here, is written not to account for a batch dimension. That's why we're not saying like we would in PyTorch like batch size and then n time steps dim. We're just taking a look at n time steps dim because a single sample to us consists of multiple time steps and the dimensionality. But layer norm, despite being used very commonly with transformers in particular, layer norm has really nothing to do with the idea of a transformer or attention or anything. Layer norm is a very generic kind of normalization that you can apply. And if I command click here and I take a look at the actual code for layer norm inside the Equinox library, which, by the way, NN is also coming from Equinox. So if I take a look at the code for layer norm, you'll actually notice if you take a look at it that it also expects a single sample. So the input is supposed to have the same shape as declared during initialization. What that means is that the input layer norm expects, or the input that attention norm in this particular case expects, is actually just dim. But what we have is n time steps dim. Now, that's okay. You'll see how we handle this in just a moment. But for now, though, we do need to figure out some kind of way to get the attention norm to operate across all the different time steps. So it's the same normalization being applied to all time steps. How do we do it? Well, here's the really fun part. vmap comes back to save us here, because as I mentioned, JAX is highly composable. So even though this function is only dealing with a single sample, our sample has multiple time steps. Attention norm doesn't know that there's this idea of multiple time steps. It doesn't even care. It just needs an array of the correct dimensionality on which to perform normalization. So what we do is we tell Equinox to perform a vmap on this attention norm layer, and then we take the output of that, which is a vmapped version of the layer, and we pass the input in. And what this does is attention norm as mentioned, internally will not know that we're operating on multiple time steps, but JAX will just make it work and the output will be, again, shape n time steps dim. And then, this is the real fun part, this entire block, multi-head self-attention, itself can then further be vmapped outside of here. And even though this code doesn't care about a batch dimension, that code would then introduce a batch dimension to this. And so, through two levels of vmap, attention norm will effectively be looking at a batch dimension, a time steps dimension, and the actual samples then, so it's got those three axes. But attention norm won't know any of it. To it, it will look like it's just operating on individual samples. But because through the call stack, we've been through two layers of vmapping, it's in practice operating on two additional axes that it doesn't even know about. And so that's the really fun part here. And I did also mention just a second ago that Equinox is nice because it doesn't have its own like vmaps and stuff like Flax. And I guess I was exaggerating a little bit. It does have this functionality called filter vmap. And so like, you know, I might just be able to use jax.vmap here. But the reason that it's nicer to just use EQX filter vmap is because of the fact that Equinox, as I mentioned, has some conveniences. And what filter vmap will do is it will strip the pie tree of this layer to only contain the portions that JAX is interested in before performing a vmap. So this is effectively equivalent. Like you can think of it as just saying jax.vmap attention norm. Like you can think of these two as effectively being the same for simplicity's sake, but in reality, what Equinox is doing is it's stripping away information from here, like say this static dim field, if that were in the multi-HUD self-attention block, stuff like that. It's stripping away all that static information. It's keeping only the parts that JAX cares about for a VMAP or for a JIT or for whatever else you need Equinox to do, and then reconstructing it internally when necessary automatically. If you look at the logic for it, it's not too complicated. Like you could have written out this logic yourself if you sort of dig through the call stack. It's not too hard. But again, the idea of Equinox is that it's giving you these conveniences that you otherwise would have to write yourself. And just like that, we have our attention layer. So we perform normalization across all time steps. We invoke our internal attention layer. We have our residual connection on the outside with the X+, and then we just do the same thing for the MLP. The MLP is even more interesting because we got to filter VMAP not only the normalization, but also the MLP itself. That's also something that needs to be VMAPed because again, attention expects many tokens, the multi-layer perceptron doesn't. And then internally, it's even more beautiful taking a look at the actual multi-head self-attention implementation, in my opinion at least. If you take a look at this, it's got some super simple code internally. This is truly one of the simplest self-attention layers I have ever implemented. It's beautiful. It takes as input just 3 parameters. The tokens that we want to attend against each other, whether or not to perform causal masking to make it so that the tokens can only see themselves and past tokens, not future tokens. And the mask. So if we had, for example, padding in the sequence and it wasn't a causal transformer, then you'd want to use that mask to make it so that we're not allowing tokens to attend to padding tokens. Over here, you can take a look at the different operations that we run against the tensors, and they all don't assume a batch dimension. So for example, when rearranging the output of the query key value projection, we don't think about this batch dimension. We just see n as number of time steps. And similarly down here, when we're worrying about, say, the causal mask, we only worry about the causal mask for a single head, and it just applies to all of them. It broadcasts normally. And then we perform our final multiplication, weighing the values according to the similarity matrix of attention, and then returning the projections on top of all those self-attended tokens. So very simple self-attention implementation, and all of this gets composed together by JAX super simply towards the end. Coming down here to the unconditional handwriting model again, the only part of this that is still just a little bit weird is this Gaussian mixture model. The rest of the architecture is pretty standard. We're not going to go too deep into the math behind the Gaussian mixture model today. I'm just going to show you the different components of it, and then in a future video we'll dig a lot deeper into how and why exactly this module in particular works. The way that it functions though is that it has a certain input size which it will project into the parameters for its distributions. You just have to tell it the number of components that you want in your final distribution, so the number of Gaussians that you want the model to parameterize. The more components you have here, the more sort of variability you're giving the model in how many different quote-unquote ideas it can have of where the pen might need to move to next. When you call this layer, it's not actually returning to you a single point. You would think it would, but it doesn't. Instead, it returns to you what I call just the output of this layer, which is all the different parameters that specify how these distributions should be shaped and the likelihood of sampling from them, which we can then use to actually perform the sampling. The sampling logic is down here. We can go into that, as I mentioned, in another tutorial in the future. Effectively, it's just leveraging those parameters in order to finally sample an x and a y coordinate that it can return to you. But the more interesting part for this tutorial is this loss function right here. The way that it works is by using this little utility function. What this utility function provides is basically given a target point x and y, so x and y here represent a single scalar point. They are the different axes of our target. And also given the parameters to a probability distribution, what this function will do is it will return to us the log probability of sampling this target from this distribution. So what that means is, say we know the x and y coordinate of where the pen should be at our next point. So we're at some point t, we know t plus 1, we know where the pen should go. That's our target over here. This is the distribution that's been output by the model. The output is the log probability of the distribution described by the model being able to sample this specific target output. So this helper function allows us in this loss function to actually look at the output of the model, look at what the target is, and then return the negative log likelihood loss value of sampling that target from that output. So let me try and boil this all down for you in just a moment here. Say you're training a super simple image classification model. The output is typically your different classes. So cat-dog classification, you'd have 2 final output values. And you'd use a, say, categorical cross-entropy loss function is what a lot of different frameworks call it. But really what it's called internally is a negative log likelihood loss. Effectively, what you're doing is you're treating the output of the model as a probability distribution, and you are trying to maximize the likelihood that the value you would sample from this distribution is associated with the correct class. So you're trying to make it so that every cat image maximizes the cat probability, and every dog image maximizes the dog probability. What this loss function is doing here is it is effectively mathematically incentivizing the model to make it more likely that given the distribution described by the model, we would sample the target that we actually saw in the data set. And if we can maximize the likelihood of those parameters resulting in distributions that sample our targets, that means we have more sensical distributions that the model is outputting, meaning we have better output generations from the model effectively. And the reason that it's the negative log likelihood loss is because log probability values are negative, at least for an individual Gaussian distribution. And so if we were just taking the regular log likelihood, we would actually be wanting to do gradient ascent, not gradient descent, because the closer these values are to 0, the closer your probabilities are to 100%. But the more negative these values are, the closer they get to negative infinity, the more likely, or that maps to a probability of 0% effectively. So the negative log likelihood loss makes it so that 0 is your target, 0 is like the best you can do, positive infinity is the worst you can do because that associates to 0% probability with negative log likelihood. And so you simply here are predicting, or you're calculating that negative log likelihood for the Gaussian mixture instead of for specific classes like cat and dog. That's the only real difference. Apart from that, it's a very similar loss function in its nature to what you would typically train even like a classification model with. It's just how we get there that's pretty different. So then, going back to our model, we then have another wrapper inside this EQX module, this loss function here. And we also have a sampling function here that allows us to actually sample data. The loss function is pretty simple. It's basically a forward function if you think about it. We're taking our sample and we're taking the inputs and targets from it. So just like any other autoregressive model, if you ever train maybe like a language model or something like that, we're saying that given our sample, and again, remember that we are ignoring the batch dimension here. That's something that took me a little while to really drill into my head. We're ignoring batch dimension. We're taking our sample, we're stripping off the very last output because the last output is our end of sequence. And for our targets, we're stripping out the very first input because we can't target the very first input to the model. That's an input, not an output. So by doing so, our inputs and targets are now of the same shape. They're just shifted one to the right and one to the left. And then from there, we simply run the data through our model and calculate our loss. So we project our input by vmapping into its embeddings. These are our actual tokens now. We then take our tokens and run them through each attention layer and finally normalize the output of the attention layers. We then perform a projection from the output of the transformer into the pen states, and we use a sigmoid binary cross entropy, this is accurate to the paper, in order to compute the loss of the actual pen states themselves. And so the sigmoid, regression real value target of 0 false, meaning keep the pen on the paper, 1 true, meaning lift the pen off the paper. And then finally here, we run our Gaussian mixture model on the outputs of the transformer and ask it, using this loss function I was talking about here, we ask it for the loss value of the model output given the target pen positions that we know we were trying to hit. Then based off of the length of the sample, we go ahead and mask out the input, or specifically the losses. We go ahead and mask out the losses that are for padding positions. And the reason we do this is because the samples all must be the same length. And so we might feed in a sample that has, say, a bunch of extra time steps at the end that are just nonsensical for padding. So this will go ahead and zero out the losses of any time step that is past that padding boundary. And that'll make it so that we don't optimize the model to predict padding values. Sampling is pretty similar. We're running all the data through the model, except instead of computing losses, we now actually run sigmoid against that pen state projection, and we actually sample from that Gaussian distribution, and then go ahead and return those values. And finally, we can get to the really important part, which is our training loop, the sort of core of this entire thing. Let's take a look at it. Okay, here's our training loop code. I'm glad to say that it's actually not too long. It's only about 120 lines long. Let's dive right in. Now, right at the top here, super simple constants. We're going to train floating point 32. For some reason, training with lower precision is obviously faster, but it does end up messing with the loss values a bit, and we don't usually converge. I'm still working on debugging why. That's despite the fact that I'm using bfloat16. So, again, code's available on GitHub if anyone notices where that loss of precision might be affecting the correctness of the math. Feel free to let me know. But apart from that, I am working on debugging that. We'll probably see the results in the next video. But moving on here, I've got one function that enables me to load the data that was pre-processed by the previous script I was showing you into a TF data dataset. Now, one of the things about JAX is that unlike other, typical ML frameworks like TensorFlow and PyTorch, they don't provide any utilities for dealing with datasets, things like batching data or loading it from disk, saving it, pre-processing it, things like this. And the reason that they stated for not providing this infrastructure is that other frameworks already do this, and there are so many of them that there's no reason to replicate all of that in a library that is primarily focused on the math and the acceleration of the math. And so using TF data is probably our best bet here. I'm used to the PyTorch pipeline personally, but I've been learning TF data because it can be a lot more efficient, a lot more easily than PyTorch's can, because PyTorch has a lot of weird quirks with the way that it works with the Python interpreter and so on. So getting the data set is pretty much just a matter of loading our pickle and loading the encoded samples and padding them and then turning them into a TF data set. That's pretty much all it is. It's nothing super complicated, so we can move on directly to our training loop. Now, the way the training loop is structured is honestly a little bit weird with respect to a lot of other frameworks, but I think it works really well once you get used to the paradigm. Let me walk you through it. So first things first, we start off by declaring a nested function within main, and all this function is responsible for is computing loss. So given a model and given a batch, so this batch, unlike normal, it's not x and y like inputs and target. Instead, the inputs are the targets because it's autoregressive. So the batch is really the samples and then the lengths of those samples. Now, the compute loss function is going to do its own vmapping. So this function finally does expect batch dimensions. So these two arrays are expected to have that initial axis that corresponds to the batching. And I'll talk about what we're returning here in just a moment. But as you can tell, what we do is simply we decompose that tuple into samples and lengths. We then call the model's loss function and we vmap it, passing it the samples and the lengths so that we can get the losses of both the pen position and the pen state. We then compute the average position and state loss, and then we return, ignore the second part for just a second, we return the sum of those two losses. So if all you cared about was that final loss value and using gradients with respect to that value, then this is all you care about, and that's you can ignore the rest. You can ignore the rest of this line. But the reason that we are returning this tuple of tuples in a way is because this first output value from the function corresponds to the genuine loss value that we will actually compute gradients against. Right? This is the value that JAX needs in order to be able to compute gradients in the first place. This second piece here is what's called auxiliary data. So JAX allows us to take a function that we're going to differentiate and return auxiliary data from it if we would like to pass out some data that's important to the caller of the function, but not necessarily important to the gradient computation itself. That's why we return these two loss values. It's so that I can log the position and state losses independently instead of just having to log the summed loss value, because that's less informative. Then we've got a train step function. So to remind everyone of the hierarchy of the training loop here, you've got this sort of larger training loop. That training loop consists of multiple epochs. Each epoch consists of running through the entire data set batch by batch. And each batch that we optimize and model against, sort of individually as a step, is called a train step. And so multiple train steps, specifically enough to go through every single batch in the data set, is what makes up one epoch. So what this function is doing is it's defining all the things that must be done in order to execute precisely one training step. So as input to the training step, we are passing it the model, obviously. We're passing it the batch that we want to optimize for, and we're also passing it an optimizer state. I'll show you what that means in just a moment. And also, for background, we are using what's called the opdax library for optimization. It's the standard. It's a really nice library. It has a lot of built-ins for different optimizers, different kinds of gradient transformations. You'll see what I mean in just a moment. So we pass it the optimizer state, and then there's a pretty complex return, but don't worry, I'll break it down for you in just a moment. So first thing we do is we invoke the filter value in grad function. Well, what is filter value in grad? Well, if I were to sort of show you the JAX equivalent of this, I think it would start to make sense. You can think of those lines of code as effectively implementing the following, JAX.value in grad. So you can think of that call actually being a call to this function instead, and I think you'd be able to sort of click together what's happening here. We're calling JAX, and we're saying, hey, for this function, I want you to give me back both the value of this function when we invoke it, but also the gradients with respect to its input. So kind of like jax.jit, jax.vmap, there's also jax.grad and jax.value in grad. And here we're saying, yeah, I want you to take this function JAX, I want you to trace it, I want you to return to me derivatives with respect to every input, that's the gradient, and the value of the outputs of the function itself. We are also informing JAX that this function does in fact have auxiliary outputs, which are these arrays here that I was talking about. And then we go ahead and invoke this transformed function with the model and the batch. The output of it, we ignore the summed loss, we grab the position loss and the state loss, which were returned from here, and we grab the gradients that were returned by JAX itself. So deleting this, bringing back our original version, we go ahead and grab the gradients, grab the position loss, grab the state loss, and from there, we can use those gradients in order to optimize, or rather update the model. So we take the optimizer, which hasn't been declared yet, but you'll see where it gets declared in just a moment. We take the optimizer, we update it using those gradients, we pass it the current optimizer state, and we also pass it the model parameters because some optimizers require access to the model itself, such as AtomW. This gives us then a brand new set of updates and the new optimizer state. We apply those updates to the model itself, and then we're done. We've completed a training step. We've got a brand new model. So we go ahead and return that model, the new optimizer state, and of course, for logging purposes, the position and state losses. So think for just a second about what the paradigm of this train step is here. What we did is we declared a function that is taking as input the model and optimizer state and returning as output the new model and the new optimizer state. That's not how you would typically think to do something like this with another framework like PyTorch, for example, where things are more stateful. When things are more stateful, like with PyTorch, you think of the model as a persistent object that exists, that we are updating, and that sort of just exists in some more global, not necessarily global, but more global context than just the training step. But because of the way that JAX works, and because of the way that it's able to sort of trace through all the operations that you're running, and think about how to perform computation before actually performing it, it's actually more ergonomic with this JAX paradigm to model a training step this way, where the model and optimizer state are inputs to this training step and also outputs of the training step. One of the other things you'll notice is that we are JIT compiling this function, and instead of manually doing that later, we're actually putting it here as a function decorator. That is another thing that you can do. You can use jax.jit, eqxfilterjit, and so on as function decorators so that you don't need to manually call that yourself later, if you know, for example, that a function always needs to be performed with JIT. But one of the other things I want you to really think about here, and sort of like absorb, is the fact that this function decorator, filterJIT, is now operating on a lot of math. Like this train step function looks small, but that's because it's composing together a lot of really advanced functionality under the covers. Not just code that we wrote, but also stuff that JAX is doing that you're probably not thinking about. Like when we take a look at compute loss is vmapping that loss function across all the inputs. Inside that loss function, we're performing attention, we're performing the Gaussian mixture, we're performing multilayer perceptrons. We're performing normalizations. Some of these operations, like the perceptrons and like the normalizations, they themselves are being vmapped over time steps. Right? Those are all operations that sort of like make up this really large computational graph. And on top of that, further, we then have JAX going in, tracing all of that, and computing a gradient function so that it can give you gradients. So all of that all together is something that JAX has a complete and full picture of when you wrap JIT around just the training step. So even just looking at this training step, wrapping JIT here enables JAX to look at the gradient computation, all of your model math, even the optimizer update, right? Even taking a look at the way the optimizer performs the math for the update itself. All of that is in the view of a single just-in-time compilation sort of context, enabling JAX to perform some really crazy optimizations that you couldn't get with other frameworks. That's sort of what's going on here, and it might start to click, why it's so important to be using that JAX JIT functionality. Later, we're going to do a quick measurement to see how fast this training loop is with and without this single line of code. So moving on from there, the rest of this is honestly pretty standard stuff, which is kind of surprising, but it's a really standard training loop. It doesn't differ too much apart from what we've just seen now. We're getting our data set, constructing the model, and then constructing our optimizer. This is the only part that might look a little bit off compared to how it works in other frameworks, but it's actually really simple and super powerful. For example, what's happening here is we're declaring our optimizer, but really what we're doing is not necessarily creating an optimizer. That's at the wrong level of abstraction, but it's a lot simpler to understand. Instead, what we're doing is we're defining a gradient transformation. We're defining a way that a gradient given from jax.rad should be transformed in some way. And in this particular case, we're telling opdax to chain two different transformations together. First of all, we're going to clip the gradients by their global norm, and this is just for training stability. And then we're going to perform an atom W optimizer on top of that. That's all there is to it. We're telling it that we want a learning rate of 1e minus 3 and a weight decay of 0.1. But it's super easy to add even way more complex functionality on top of this. If you've ever tried to implement, for example, an exponential moving average of weights in PyTorch, you'll know that it's incredibly painful. And people who are super familiar with PyTorch will probably say it's not that hard. Realistically, you can implement EMA in PyTorch, right? But I know from firsthand experience that it's not really that easy. It would be quite a bit of code, and especially when you get to large-scale distributed training, you got to think about how you're actually collecting those weights and all sorts of things. Whereas here, and of course this is a simple example, but even the simple example in PyTorch would be way more complicated than this, because here all I'm going to have to do is say opdax.ema, and then I give it my decay, which say I said like 0.8, and suddenly that's it. Now my weights will get an exponential moving average. And that's just because JAX sort of represents, and Equinox and opdax, all these different frameworks, they represent the process of optimization and gradient transformation and your model's forward process and all of this at the correct level of abstraction, which is very low level. And that's why a lot of this code will seem a little bit more intense than it needs to be. A lot of this training loop code, for example, could be cut out if I were to use PyTorch Lightning or something. But being at the right level of abstraction makes things a little bit more complicated in terms of your training loop being a bit more verbose or manually moving keys around for random numbers and stuff like that. But being at that right level of abstraction also then gives you capabilities like just throwing a single line of code in for exponential moving average and not needing to worry about having to jerry-rig it into a framework that really doesn't like the idea of you modifying state in this way. So that's really an advantage that you get by accepting some of the additional slight complexities and verbosities of a framework like JAX. And then from there, we can go ahead and take this optimizer that we've declared and actually initialize it with the model. And this EQX filter is doing something similar to what I talked about before. It's stripping the pie tree of all the stuff that's irrelevant to being optimized and keeping only the stuff in there that's like actually JAX arrays, or at least array-like. That gives us our optimizer state, and that's something that we then go ahead and pass into the function and so on. But this optimizer is just a generic series of gradient transformations that's stateless. And so we can simply invoke this as like a non-local, parent function variable here to get optimizer.update inside of our train step. And then from there, we simply have our training epoch, super standard stuff. Our model and optimizer states are declared as non-locals because we're going to update them. We're going to go ahead and update our inference mode to be false. This is important for things like batch normalization and dropout if we were using them, because then they would need to know that they actually have to activate and do things like update the running mean or perform dropout. If I were to set inference mode to true, then for example, dropout wouldn't apply, stuff like that. And then we go ahead and loop through our batches, perform training steps, log our loss, and log it at the end one last time. Finally, we just go ahead and for each epoch, invoke train epoch and serialize the model out to a file, and that's all there is to it. That's our training loop. And just like that, in theory, we should be able to go ahead and train an unconditional handwriting synthesis model. Now, I'm happy to say that for almost the first time ever, I've, ironically enough, found it simpler to train a model on an Apple Silicon machine than to train it on an NVIDIA GPU, which, again, kind of ironic, but it's because this Mac has a lot more RAM than the vast majority of consumer, and actually really any consumer NVIDIA GPU, any NVIDIA GPU that's easy to get your hands on at least. And so training this transformer on macOS is actually super simple. I'm using Apple's kind of experimental JAX Metal plugin to make JAX capable of running its compiled code on Apple Silicon GPUs. And so giving it just a moment to load the dataset, as you can see, it's already training our transformer with a pretty decent rate of speed. And keep in mind, this is during the fact that I'm also screen recording on the same machine. We're already getting 3.2 iterations per second, which is a decent amount. It's actually not too far off from when I'm not recording. So really quickly, let's go ahead and compare some speed here. We're getting approximately 3.2 iterations per second with JIT compilation. If I go ahead and stop training here for just a second, and I comment out the filter JIT here. So train step is no longer being JIT compiled. It is simply running on its own without any real JIT compilation. It's all just eager. So now let's take a look at about how fast this is going to run on the Apple Silicon GPU. Also, you might want to notice how we did not in our code in any place specify like what device this should run on. The fact that it should run on Metal or on CUDA or whatever it is. And that's because JAX handles it automatically, which is honestly sometimes a bit frustrating. I don't actually really like how automatic and how magical JAX is with the way that it handles like devices and so on. That's still something that I'm sort of getting my head around and understanding about the way that JAX performs operations internally. But it is really convenient once you do get used to how JAX operates. So taking a look at the current rate of training, it's taking multiple seconds per iteration, about 2 full seconds per iteration. So we went from 3 iterations per second, over 3 iterations per second, to over 2 seconds per iteration, removing that JIT compilation. That's how much of a difference it makes, because that's the difference between just individually running operations naively with no real understanding of what you're doing versus telling JAX to really look into all those operations, compile them down into a single compiled function, and then invoke that optimized code. So now let's go ahead and finally, we're almost done here, take a look at how we can predict with the model. And running predictions through this model is actually really simple. All it consists of is, once again, initializing the model, asking Equinox to deserialize the checkpoint into the model weights, and then from there, JIT compiling our sampling function. So over here I had to create a lambda function because the key for the random number generation is itself unfortunately it's a keyword argument. And so because FilterJIT doesn't support using keyword arguments, we have this lambda to wrap it so that we can pass the keyword argument in manually. But again, this is just one of the nice things about JAX and Equinox is, for example, it doesn't care about the fact that you're using a lambda here and not a real function. All it cares about are the operations that get traced. And if you've worked with Python's multiprocessing, for example, sometimes lambdas are weird in multiprocessing pools. They can't be pickled, stuff like that. JAX doesn't care. It's not doing any weird tricks with the Python interpreter. It's not leveraging hacks to try and understand what your control flow is. It is simply tracing through all of your array operations, and that's all there is to it. And that's the fun part. That internal simplicity translates into a simplicity during like the process of writing code as well, because you're not trying to reverse engineer what it could be doing to get wrong with your logic, like torch compile. And then from here, we have a super simple autoregressive inference loop. You'll notice over here some of the quirks around mutating JAX arrays that I was talking about. Because JAX arrays are immutable, I cannot, for example, just do something like samples I plus 1, 0 equals x. This is invalid because I would be mutating that original array. Instead, the syntax for it actually looks more like this. Samples equals samples.at.set. So it's just a little bit of something you got to get used to. But it is there are valid reasons for all these quirks to JAX. And we'll get into how you can make loops like this more ergonomic using actual JAX functionality and so on in the future as well. But after this simple autoregressive inference loop, we then create that stroke set from the time steps that were output by the model, and then we go ahead and render and show the stroke set. So how about we go ahead and run this in real time and see if we can get a valid prediction. So I've got this currently with some cooking show magic to run on a checkpoint that I've already generated after just 2 epochs of training. And just like that, there we go. We get generated text or handwriting, or at least it looks something like handwriting if the person doing the writing didn't know what they were trying to write. You can start to notice some patterns here, maybe. Like, there's a couple letters you can kind of make out, like maybe this is trying to write a Y over here. But one of the fun parts, and this is something that I actually really like, if I rerun the script, watch this. This is magical, what's going to happen here. I'm going to rerun the script, and just like that, same thing. And the reason I care about the fact that this is the same thing so much is because, well, in a lot of other frameworks, you would really have to try to make it deterministic. With JAX, I didn't try, it just was deterministic. And it was deterministic because I just used a single random seed here. If I simply changed this random seed, and for example, instead of 42, let's just say I did like 60, and I go back, suddenly I'm going to get a different generation because we're going to choose different random numbers when we're sampling from the Gaussian mixture model output. And just like that, we get a different series of squiggles. But as you can see, clearly the model did in fact learn how to squiggle, in this case, and the model was able to learn in a way that was reasonably sensical. So you can sort of make out the initial bits of some letters. It's just clear, obviously, that the model A does not know what it's writing, and B, and this is sort of the more concerning part for me at least, the model never decides to pick up the pen currently. That is a limitation I haven't gotten around just yet. But I'm sure that in the next tutorial, as we extend upon this code base to predict longer sequences and to be conditional, that we will solve these issues and get it to generate more realistic text as well. Now, this model does not use any positional encoding because of the fact that it is a causal transformer. I've done a lot of research into the positional encodings that would be appropriate for this kind of task, and because of the fact that causal transformers have this causal mask and they can sort of like manually count out the number of tokens that have occurred previously, in theory, we don't actually need positional encoding for this transformer. And so, as you can see, even for longer sequences, like going up to 1200 time steps, it still seems to be reasonably sensical. The training script does cap out the data samples to max at 1200 steps, but still I'm reasonably certain that it should be able to generalize past the 1200 boundary, so going up to 1500, for example. If I run another prediction, it should be able to give us data or a sample that's mostly on par with what we have right now. And there we go. As you can see, the sample is mostly sensical, starts off pretty squiggly, continues to be pretty squiggly, gets a little bit more abstract almost towards the end, but as you can see, it hasn't like gone off the rails and just completely exited the distribution of where we approximately were. So no positional encoding does not seem to significantly hinder the model's ability to understand the fact that this is a time sequence. So with that, we've trained an unconditional handwriting synthesis model using JAX, using Equinox, using a causal transformer decoder-like architecture, but no cross attentions. And that brings us to the end of today's tutorial. I really hope you enjoyed, and I really hope you enjoyed getting into the world of JAX and how it works. In the next couple videos, we are going to make this model significantly more advanced, get it to support, of course, conditional synthesis and other sorts of features that I think are going to be really fun, and fix some of the rough edges that currently exist in the code as well. In the meanwhile, feel free to dig into the repo in the description below. Feel free to comment if you have any questions, suggestions, or feedback. I'd love to hear from you. Apart from that, make sure to like the video if you did enjoy it, subscribe to the channel as it really does help out a lot, and turn on notifications so you're notified whenever I release new content just like this. And with that, thank you everybody for joining, and goodbye.